At about 8:10 on the morning of December the 7th, 1941, USS Nevada took a hit forward on the port side. Soon after, as she struggled toward the channel, the officer in command faced a binary choice that would define the rest of his life. His ship was the battleship Nevada. She was the only battleship that managed to get underway during the attack. She was moving, but she was bleeding. A Japanese aerial torpedo had struck the hull and opened a massive vent in the port side. The ship was taking on water fast. The captain looked at the narrow channel ahead. It was the only exit route for the Pacific Fleet. If the Nevada succumbed to her wounds and sank in that deep water, she would become a 29,000-ton steel cork bottling up the entire Navy inside Pearl Harbor. His options were stark. He could try to run the gauntlet to the open sea and risk sinking in the channel, or he could deliberately drive his ship into the mud. One choice offered a slim chance of escape. The other guaranteed the loss of the ship as a mobile fighting unit, but saved the strategic mobility of the fleet. He ordered the helm over. He was going to ground her. To understand why this decision was necessary, we must look at the physics of the impact around frame 41 to 42. The weapon was a Type 91 aerial torpedo, specifically modified for shallow harbor work. It struck the Nevada on the port bow about 14 feet above the keel. The explosion did not just punch a hole, it tested the entire architectural philosophy of the ship. The Nevada was the first superdreadnought of the Navy designed with a sophisticated layered defense system. This system is built on the principle of sacrificial voids. Between the outer skin of the ship and the vital dry magazines, there are multiple vertical bulkheads. The outer layers are empty or filled with liquid fuel meant to absorb the hydraulic shockwave of an underwater explosion. The energy of the blast is supposed to dissipate as it crushes these outer layers, losing its lethal force before it reaches the inner holding bulkhead. On paper, the geometry is sound. It is a series of steel curtains designed to deform so the inner citadel remains intact. On December 7th, the system technically worked but physically failed. The innermost torpedo bulkhead at frame 41 held its shape. It did not shatter. However, the shockwave was so violent that it warped the steel plates and sheared the rivets connecting them. The watertight boundary lost its integrity not through a catastrophic breach, but through thousands of microscopic failures along the seams. Water began to bleed through the steel joints. The ship developed a list of 4 to 5 degrees to port. This is where the engineering reality collided with the operational crisis. The Nevada was not just fighting gravity, she was fighting time. As the ship moved toward the channel entrance, the water pressure against that compromised bulkhead increased. The flooding was progressive. Counter-flooding measures were taken to correct the list, but the ship was becoming heavy and sluggish. She was settling deeper into the water. By about 9:25, Nevada was forced onto the coral ledge at Hospital Point. The bottom here was a mix of mud and hard coral. It was not a soft landing. Driving a battleship onto a shelf is a violent mechanical event. The momentum of 29,000 tons of steel does not stop instantly. As the keel ground into the seabed, the hull groaned under extreme torsion forces. The bow bit into the ground while the stern remained afloat, swinging in the current. This created a hogging stress where the ship bows upward in the middle, threatening to snap the keel. By putting her on the beach, the captain solved the channel problem. The exit was clear for the rest of the fleet, but he had traded a tactical problem for a salvage nightmare. The Nevada was now a stationary target. The enemy bombers returned and pounded the stationary ship with 5 direct hits. The structure was ravaged. Fire swept through the forward superstructure. The ship was now resting on the bottom, but she was not safe. The water outside was shallow, but the water inside was rising. The compromised torpedo bulkhead was leaking continuously. The pumps were fighting a losing battle against the ocean. The salvage engineers arriving on the scene saw a ship that looked stable but was internally chaotic. They prepared to fight the water and the steel. They did not know that the most dangerous enemy on the ship was not the Japanese aviation, but a biological reaction starting deep in the provision rooms. The ship was about to turn toxic. The most dangerous trap on the Nevada was not a hidden Japanese bomb or an unexploded torpedo warhead. It was an invisible shadow hanging in the air of the lower decks. By early February 1942, the salvage teams had stabilized the external position of the ship, but the internal environment had become hostile to human life. The ship was no longer just a flooded vessel, it was a decomposing biological machine. The problem began with the provision load. When the Nevada sortied on December 7th, she was fully stocked for war. Her cold storage and provision rooms were packed with perishable stores meant to sustain a war deployment. Her dry stores held large quantities of paper products, packaging, and general stores. When the torpedo struck at frame 41 and the bombs tore open the forecastle, the electrical grid failed. The refrigeration units stopped. Then the tropical heat of Pearl Harbor took over. The lower decks were sealed damp and warm. This created the perfect incubator for anaerobic bacteria. The meat began to rot. The paper and cardboard turned into a gray sludge. This organic soup began to generate massive quantities of hydrogen sulfide gas. This is a chemical agent that is both heavier than air and ruthlessly toxic. It sinks to the lowest compartments, pooling in the pump rooms and bilge spaces like invisible water. The salvage crews received a visual warning that something was wrong with the chemistry of the ship. Deep inside, surfaces were found darkened and stained in a way that was consistent with sulfide contamination rather than simple fire soot. The ship was advertising its toxicity before the men could measure it. On February 7, 1942, the chemistry turned lethal inside a confined trunk space. Lieutenant James S. Clarkson was overcome by hydrogen sulfide. Machinist Mate DeVries reached him first and later died as well. In all, 6 men were overcome, proof that Nevada had become a chemical hazard zone as much as a salvage job. They likely never knew they were in danger. Hydrogen sulfide has a cruel physiological trick. At low concentrations, it smells like rotten eggs, a clear warning to stay away. But at high concentrations, it paralyzes the olfactory nerves almost instantly. The sense of smell vanishes. The victim assumes the air is clear just before the gas blocks the ability of the cells to process oxygen. The 2 men collapsed. They died in the darkness of the pump room, killed by the rotting food of the crew they were trying to save. This tragedy forced a total change in the salvage protocol. The Nevada was treated as a hazmat zone. Gas masks became mandatory. Ventilation blowers were rigged to force fresh air into the lower decks, displacing the heavy gas. The rotting meat had to be removed by hand, often by divers wading through the toxic sludge. The paper sludge had to be shoveled out in buckets. The gas also attacked the divers. The hydrogen sulfide dissolved in the water, creating a weak acid that irritated the eyes and skin. Divers surfaced with severe burning sensations and temporary eye and respiratory irritation. The salvage master had to enforce strict time limits on exposure. They were fighting a war on 2 fronts. One was against the ocean trying to crush the hull. The other was against the chemistry trying to poison the crew. With the ventilation systems roaring and the gas levels finally dropping, the engineers could turn their attention back to the steel. The biological hazard was under control, but the structural problem was getting worse. They needed to seal the bomb holes and the torpedo breach to pump the water out. They looked at the damage reports and realized that patching the Nevada would require 2 completely different engineering strategies, one for the small holes and one for the giant wound that had started it all. To seal a battleship underwater, you cannot simply fight the ocean with brute force. You must trick the ocean into helping you. The salvage engineers working on the Nevada understood that water pressure is a crushing weight, but if manipulated correctly, it becomes the most powerful clamp on Earth. The ship was riddled with holes from the 5 bomb hits and the single torpedo strike. Each wound presented a unique geometry problem. The steel skin of the hull was not just punctured, it was torn and twisted outward like shrapnel. Several of the bomb holes along the hull and weather decks presented the first challenge. The jagged edges of the steel projected outward, preventing a flat plate from sitting flush against the hull. The divers could not easily burn away the jagged metal in the zero visibility mud. The solution was a specific piece of hardware known as the window frame patch. This device is a marvel of improvisational engineering. It consists of a rigid, steel box frame that is slightly larger than the hole. The genius is in the rim. The edge of the patch is not steel, but a thick collar of soft wood, often pine or fir, wrapped in canvas and soaked in sealing compound. This wooden gasket is designed to crush. The installation process is a delicate ballet in the dark. A diver inside the flooded compartment pushes a T-bolt through the jagged hole to the outside. A diver outside catches the bolt and guides the window frame patch onto it. They tighten the nuts just enough to hold the patch in position against the hull. Then they give the signal to the surface to start the pumps. This is where the physics of the cofferdam effect takes over. As the pumps suck the water out from behind the patch, the pressure inside the hull drops. The pressure outside remains constant at the ambient depth. This differential creates a massive net force pushing inward. The ocean itself shoves the patch against the side of the ship with thousands of pounds of force. The soft, wooden gasket bites into the jagged steel irregularities, molding itself around the damage to create a watertight seal. The deeper the hole, the harder the ocean pushes. The patch does not hold back the water holds the patch. The window frame patches worked perfectly on the bomb damage. One by one, the smaller wounds were sealed. The pumps cleared the forward compartments, and the ship began to regain some of her buoyancy. But the engineers knew these were just the warm-up acts for the main event. The torpedo hit at frame 41 was a different class of destruction. This was not a hole, it was a cavern. The breach was roughly 30 feet long and 18 feet high. It spanned multiple deck levels. A standard window frame patch would simply buckle under the load. The salvage team designed a massive wooden patch to cover the wound. It was a complex structure built on the surface, shaped to match the curvature of the hull at frame 41. It was built like a retaining wall reinforced with heavy timber strongbacks and steel tie rods. The construction of this main patch took weeks. It had to be weighted to sink, then maneuvered into place by cranes and divers working in coordination. It was a heavy industrial operation performed on a sliding mud bank. The theory remained the same. They would position this massive wooden shutter over the torpedo hole, secure it with hook bolts, and let the pumps create the vacuum that would seal it tight. By early February, the great wooden patch was ready. The divers guided it down into the murk. The bolts were tightened. The engineers believed they had rebuilt the side of the ship. They were ready to dewater the main torpedo voids. They fired up the main pumps, expecting the water level to drop and the ship to rise. They were about to discover that the steel of the Nevada had one final surprise for them. The salvage of a battleship is often a war between idealized geometry and physical reality. On the blueprints, the hull of the Nevada is a smooth, continuous curve of steel. But the ship resting in the mud at Hospital Point was no longer the ship on the blueprints. She was caught in a geometry trap. The seabed was uneven, and the weight of the water-filled hull had forced the keel down into the coral shelf. This created a subtle but critical distortion along the entire length of the ship. The steel frame was under tension, twisted by the leverage of the stern swinging in the current. This invisible distortion revealed itself the moment the pumps were activated behind the massive main patch at frame 41. The engineers expected the water level to drop. It did not move. The pumps were pulling thousands of gallons a minute, but the ocean was replacing it just as fast. The seal had failed. Divers went back into the water to inspect the perimeter of the 30-foot wooden patch. What they found was a failure of the steel itself. The torpedo explosion had not just punched a hole. It had exceeded the yield strength of the surrounding plating. Steel is elastic only up to a point. When subjected to the violent shock of a warhead, it behaves like plastic. It flows. The hull plates around the impact zone were dished inward, and the edges of the tear were curled outward like peeled fruit. The side of the ship was now a wrinkled topographic map of ridges and valleys. The giant, rigid wooden patch could not conform to this ruined surface. There were gaps as wide as a man's arm between the patch gasket and the hull. The wooden seal mentioned earlier could bridge inches, but it could not bridge feet. The vacuum clamp effect could never engage because the vacuum could never form. The patch was dead weight. This failure forced the salvage master into a corner. They could not seal the outer skin. The hole at frame 41 would remain open to the sea. The Nevada would have to be refloated with a gaping wound in her side. The only thing preventing the ship from sinking again would be the internal torpedo bulkhead. This was a terrifying reliance on a compromised component. The inner bulkhead had survived the shock, but it was no longer watertight. It was designed as a sacrificial layer, a shock absorber, not a primary hull. Now it had to do the job of the main armor belt. The engineers shifted their focus from the outside to the inside. If they could not block the water at the skin, they would have to reinforce the inner wall. Teams of divers and carpenters descended into the flooded void spaces behind the torpedo bulkhead. They began a process known as heavy shoring. They built a complex lattice of heavy timbers, bracing the leaking steel wall against the uncompromised structure of the ship further inboard. They used wedges and hydraulic jacks to preload the timbers, creating a mechanical skeleton that would support the steel against the crushing weight of the ocean. They caulked the weeping seams with lead wool and oakum, trying to stem the flow of water through the popped rivets. It was a calculated gamble. When they started the main dewatering pumps for the refloat attempt, the pressure on that damaged bulkhead would skyrocket. The ocean would be pushing against it with millions of pounds of force. If the shoring slipped, or if the steel fatigue was worse than predicted, the bulkhead would collapse. The ocean would rush into the dry center of the ship, and the Nevada would capsize in seconds. The patch was gone, the safety margin was gone. The only thing left was the math and the timber shoring holding back the Pacific. On February 12, 1942, the salvage window opened. The engineers had spent over 2 months fighting the gas, the mud, and the distorted steel. Now they had to prove that the laws of physics were on their side. The plan was simple, but the execution was a high-wire act. They would pump the water out of the hull faster than it could leak back in through the shored-up bulkheads. If the math was right, the ship would become light enough to break the grip of the seabed and return to the surface. The operation began with a synchronized roar. Dozens of 10-inch and 6-inch salvage pumps were scattered throughout the ship. When they engaged, the vibration turned the steel hull into a trembling drum. The water levels inside the flooded compartments began to creep down. But refloating a grounded battleship is not just about removing weight. It is a battle against the phenomenon of ground reaction and mud suction. Buoyancy is a vertical force. Archimedes taught that a body immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced. For the Nevada to float, the water she pushed aside had to weigh more than the ship herself. But there was a hidden variable. The ship was not just sitting on the bottom, she was adhered to it. The mud of Pearl Harbor is a thick, clay-like substance. When a 29,000-ton hull settles into this matrix, it presses the water out from underneath the keel. This creates a seal. To lift the ship, the buoyancy force does not just need to equal the weight of the ship. It must exceed the weight plus the suction force of the mud. It is like trying to lift a boot out of deep muck. You need a surplus of energy to break the vacuum seal at the bottom. The engineers had to lighten the ship aggressively to generate this surplus lift. They had already stripped the ammunition and fuel. Now they were removing the ocean itself 1 gallon at a time. As the pumps ran, the ship began to talk. Steel groans and pops echoed through the empty spaces as the hull frame adjusted its load paths. The divers and workers monitoring the internal shoring watched the timber braces with intense focus. The wooden struts were the only things preventing the ocean from crushing the torpedo bulkhead. If the ship shifted violently as she broke suction, the shock load could snap the timbers. The bulkhead would fail, and the ship would plunge back into the mud, likely rolling over in the process. Hour after hour, the water level dropped. The gauges showed the ship was getting lighter. Then came the moment of release. It was not a sudden violent pop, but a sluggish lurch. The stern, which had been floating free, began to align with the bow. The heavy nose of the battleship lifted out of the coral and mud. The suction seal broke. The Pacific Ocean rushed into the space under the keel, equalizing the pressure. The Nevada was no longer a part of the geography. She was a ship again. She was floating, but she was listing. The damage was asymmetrical, so her buoyancy distribution was uneven. She hung in the water with a heavy, lean dependent entirely on the pumps to stay afloat. If the pumps stopped, she would sink in minutes. Tugs moved in to secure lines. There was no cheering. The crew was exhausted. They had logged over 1,500 diving hours in toxic water to reach this point. The salvage master looked at the waterline. It was holding. The internal patch, the wooden shoring, and the constant pumping were maintaining equilibrium. The Nevada was back in her element. She was a wounded animal, bleeding and unstable, but she was alive. The question now changed from whether she could be saved to what could possibly be done with a ship this broken. The salvage phase was over. The resurrection phase was about to begin. On February 18, 1942, just 6 days after being pulled from the mud, the Nevada floated into dry dock number 2 at Pearl Harbor. As the caisson gate closed and the water was pumped out of the basin, the true scale of the damage was revealed to the open air for the first time. The torpedo damage around frame 41 to 42 was on the order of 50 feet long and roughly 25 feet in depth. The steel plating was shredded. The interior compartments were packed with oil-sodden debris and the black residue of the toxic gas. To the casual observer, the ship looked like a total write-off. She was old, slow, and broken. But the Navy saw something else. They saw a hull that was fundamentally sound. In the calculus of global wartime is the most expensive commodity. Building a new battleship takes 3 to 4 years. Repairing and modernizing an existing hull takes less than 1. The decision was made. The Nevada would not be scrapped. She would be resurrected. After temporary patches were welded over the wounds, the ship steamed under her own power to the Puget Sound Navy Yard in Washington State. Here she underwent a process that defines the difference between repair and modernization. The engineers did not just put her back to her 1941 configuration. They stripped her down to the deck. The heavy tripod masts were cut away. The old superstructure was removed. This illustrates the engineering concept of the weapons platform. A battleship is essentially a floating steel barge designed to carry heavy ordnance. The hull provides buoyancy and the engines provide mobility, but the fighting capability is modular. The salvage of the Nevada allowed the Navy to treat the ship as a blank slate. They kept the 14-inch main guns, but replaced almost everything else. They installed modern fire control radar, which allowed the ship to see in the dark and fire through smoke. They welded on massive blisters to the hull to improve stability and torpedo protection. They covered the decks with dozens of 40mm anti-aircraft guns, turning the ship into a porcupine of defensive fire. When the Nevada emerged from the yard, she was a new ship in an old body. She was shorter and wider than the modern fast battleships, but she was lethal. The return on investment for the salvage operation became clear in 1944. On June 6, 1944, the ship that had been sunk in the mud of Pearl Harbor was sitting off the coast of France. The Nevada used her 14-inch guns to break the German defenses at Utah Beach during the Normandy landings. The German shore batteries bracketed her with shell fire, but the veteran crew did not flinch. The ship that had been the primary victim of the opening day of the war was now the primary hammer on the day of liberation. She did not stop there. The Nevada transferred back to the Pacific to support the invasions of Iwo Jima and Okinawa. She used the same guns that had been silent at Pearl Harbor to clear the path for the Marines. She was the only battleship to be present at both Pearl Harbor and the Normandy landings. The salvage of the Nevada was a triumph of technical logic over despair. The captain who grounded her at Hospital Point saved the channel. The divers who braved the toxic gas saved the hull. The engineers who designed the patches saved the buoyancy. And the strategists who ordered her reconstruction saved a vital asset that helped crush the Axis powers. The ship survived the war only to face one final test. In 1946, she was used as a target ship for the atomic bomb tests at Bikini Atoll. She survived 2 nuclear blasts and still refused to sink, remaining afloat until she was finally put down by naval gunfire in 1948. She was a ship that simply refused to die. The salvage operation at Pearl Harbor was not just about recovering steel, it was about recovering national will. The Nevada proved that what is broken can be forged into something stronger than it was before.